Hello, my name is Campbell Timms. This is my submission for assessment task 3, coding task 2. Um, Basically, the whole point of this coding task was to create a tool or utility based on your program. So in my case, I'm doing a Bachelor of Science majoring in physics. It's basically wanting you to create a program, tool, or utility that you can use within your own field. Um, so there's obviously quite a few different requirements for this um, assessment, but I'll just go straight through into the program. So just for a bit of background, I was taking a quantum physics subject this semester, so I was particularly interested in creating a simulation, a quantum simulation. I've been a part of my subjects already to create these quantum simulations, so I just wanted to take what I already had and extend that further. And in particular, one of the areas we looked at this semester has been the hydrogen-like atom, in which we solved the exact case with the Schrödinger solution. And uh, so we solved the hydrogen-like atom using the radial function and a potential for the hydrogen atom in 3 dimensions in spherical polar coordinates. Because the wave function for the hydrogen atom obviously is based upon a proton with a bound electron, and we were mapping I wanted to make a probability distribution of the electron orbitals, and that was done with this radial function here um, and the wave function for the hydrogen atom of r theta and phi. It creates sort of these looking images here, in which I can go over to here, and you can see for every single case for different orbital configurations, we could plot um, these electron orbitals. Um, so that's sort of how this relates to um, my study. What I initially want, and that's exactly what I wanted to do with this simulation. So um, I have my code here. So you'll find a file like this, and it has the Python code in it already. This was just the criteria for my assignment. And then you have these two text files here. If you open those, one is a README, and it basically just tells you how to run this software. And I'll just quickly go through that now and show you an example. So what you want to do is open this other text file, which is here. This basically has all the different sort of parameters you might want to change or use um, to create your sort of image of these, or the simulation of the electron orbitals. Um, you have obviously, you can change the resolution. Um, if you want, you can change, what values you want to put in for electron mass, a bunch of other fundamental constants. They're already placed in here already. I guess the only things you would mainly be changing would be the resolution and the quantum numbers. The quantum numbers determine what kind of electron orbital you have, and see here. So you can see for n equals 1, you get this sphere. For n equals 2, you get this sort of double-barreled sort of spheres and donuts. And as you go up, you can see they just get a lot more complicated. And the ranges for your values you could put in are listed in this README. They are the quantum number ranges so n is an integer, increasing from 1 to infinity, or not infinity, but is an integer starting from 1. L is an integer that goes from 0 to n minus 1. So whatever your highest value of n is, one below that. And m is related to L. M can be the negative of your L number, and that m could increase all the way through to a positive of your L number. So it goes through that range of values to your L. And you can see that as it's demonstrated here, where all of these are for n equals 3. These 3 are for when L equals 0. These 3 in the middle are for when L equals 1. These 3 at the bottom are for when L equals 2. And then as you go across, you can see how m changes from, in the initial case, 0 as L equals 0 in all 3 cases, to m equals -1 to 0 to 1, -2 to -1 to 0 to 1 to 2. So it spans that range of L. If you would like to run the program, like I said, all you have to do is change whatever variables you want to use. In this case, I'm going to be setting the resolution to 50 and have this sort of configuration here. This code takes quite a while to run. So what I've done is, before I recorded, I've run the simulation already. So this is the output from the code, as you can see. And what it will do is create a image in the same directory as you have the Python file, and you can open that image there. So this is for n equals 50. You can see we have this image of the hydrogen atom as it expands. And you can see as you get further away from the center, the probability distribution lowers to a gradient. You can compare this is for psi equals 542, and then if you go down here, so n equals 5, and the L equals 4, so it's down here, and m equals 2, so it's this image here. This Python file will also find you that image and then put it and save it in the same directory as well. So you can compare the simulation to the ideal. So what you can find is that you can see how they're rotated across different axes, but they do show and have a similar form. Mine have sort of concentric rings based on how I plotted it, where I was mainly just showing the real part, whilst this is the ideal scenario. We can plot both the imaginary and the real part of the wave function. In terms of the design of the code, I'll just go through that now. So like I said, I made sure you could edit all your values you needed in here. So this opens the text file, reads it, and runs the code within it. If for whatever reason you mess up or the file, it's okay. It'll produce this sort of sample plot, or if it can't find the file, it'll still produce the sample plot if the error is made. Otherwise, the rest of these all are based on first using these equations and creating the framework to be able to make these images here. So the first thing what we wanted to do is create an area and a space to plot these images. So what I ended up doing is this is probably more accurate. I create this first set of this first code block, this X, Y, and Z, creates this array. So I first plotted each of the faces and then multiplied them together, creating this 3D space as an array. Because a lot of the equations in calculating the hydrogen atom use r theta and phi. I converted all my x, y, and z's into a combinations of these r, theta, and phi values, which I can use in calculating the hydrogen wave function. Down here, there was a few corrections that I needed to make on these functions, but they should, other than that, they should make sure the code runs smoothly. This hydrogen wave function block here, basically, I've put in a lot of resources here, linking to the equations which I mainly used. They're mainly to do with this psi of n, l, and m, which is a part of the radial function, and the spherical harmonic, which is this r value here, and I believe this is this is the r value, and I believe the spherical harmonic is down here, and I've linked to that in my code. Moving along, basically these do a bunch of calculations to be able to return this psi of n, l, and m, which you find is here, this psi n, l, and m. So running this function, creating a wave function onto the 3D space of the set quantum numbers, produces this array. So in order to, and then this next code block ends up doing these plots. So this is the visualization element of it. So I've made this array, and I've got all these values within it. So what this sort of code block does is that it goes through these sort of ranges from 0.15 to 0.2 to 0.25. Just as a step, I've used a list here. You can see that in this for loop, it increases by this min-max range, which is these here. So it goes through different ranges of different values of the equation, and it colors them in. And I've set the different colors here. And I've also given them an increasing transparency as it gets more probable to find the electron in the probability density function. So that's how I've sort of created this image. Obviously using this for loop and with the large data set we have, this creates the largest bottleneck in the code. It takes probably the longest time, having to go through them quite again, as well as even still the creating the wave function itself does take quite a long time. The last part was this web crawl function, where this basically finds this web page, finds the specific n, l, and m numbers that you've inputted, finds the associated image with that, and then downloads that image for you so you can view it. Last thing I'll do is I'll just quickly run it for you in the recording. I'll just change the resolution down so it won't be as detailed as this, and then I'll do a much simpler quantum numbers. So if I go 2, 0, and 0, I should be looking to get 2, 0, and 0. Maybe I'll go 2, 1, and 1. I want to get that donut. So I go 2, 1, and 1. Oops. Then make sure to save the file so it updates the text file. So then what you want to do is, like I said, I just have my code up here in this text editor here, so my spider, and then I'll just run that. Hopefully it doesn't take too long, and what you should find is that we can see here, it picks up this image of the donut, and it creates this image here. Obviously, this is actually quite a low resolution, so there's not much. Uh, this doesn't look quite as well as this sort of perfect donut. But as you increase the resolution, it actually creates a much better indication of the theoretical values and what the theoretical images would be. The last thing I would like to say is I wouldn't have been able to do this assignment without help from another RMIT student. Greg did some 3D visualizations of the hydrogen wave function and the probability distribution as well. I had quite, I was quite inspired by him and has made this myself in Python. He also helped me out with some areas. Um, Otherwise to note, all this code is of my own creation. Through looking through most of the documentation in all the sort of libraries I used, all these libraries are standard as a part of the Anaconda packages as well. So it should be able, and anyone should be able to run it, as long as they're using a Anaconda supported Python editor. Um, I also will note the use of AI in terms of uh, asking it questions. It is very, very useful, especially when coding. Just trying to find the correct sort of functions and to do areas of code. It isn't able to write large blocks of code, but it is very helpful in putting you in the right direction and helping you write the code. It definitely saved my behind a few times trying to code this project. Other than that, I think I've covered everything that I've needed to. I apologize if the content is a bit heavy, but I hope this is a good demonstration of um, the program. Yep. Thank you.